Back at it again. The same GLO point as last weekend. Same deal. Going to be going out to Kitt Peak there. We're going to be sighting some Kitt Peak National Observatory. But today, I've got the powerhouse. I've got the Wild T3. Let's get it done. Instrument height is, drum roll please, looks to me as a 473. 473. There is my plate level. Took it through all the different quadrants. This instrument is plumb. I'm looking at a 90-12-34. This T3 is pretty tough to This is an 89, 40, 49.9.
Morning.
Morning.
Okay.
A 90, 40, 35.7. '89, 40, 44.4. It's getting tough to collimate the target, as you can see. There it is. That wraps up my 5 angles. Now it's time to run the computations. So here are the field notes from that observation this morning. Sunday, August 17th at approximately 6:10 a.m. is when I started turning the angles. The mark that I was set up on was a brass cap or bronze disc. It was a General Land Office with a PID of CG1062, I believe that is. So you can go look that up on NOAA. Here are the coordinates associated with that point. That is the longitude and latitude, and that is the elevation of that point. Add the height of the instrument, which was a 473, bringing the total to a 3304.73. The target was Kitt Peak National Observatory. There's the PID associated with that bronze disc that I was sighting. It's up there on an outcrop at the summit next to the large observatory. These are the coordinates associated with that point. And when you pull up, you can use the Haversine formula if you like, or any distance calculator to figure out what the distance is between those 2 points. The elevation of that point is 6,886 feet, and that distance is 47.578 miles. And this is that in feet. Just makes it easier to calculate your triangle. Now I turn these angles with the Wild T3. Now the Wild T3 is much different than the T2. The T3 reads in zenith angle only. Now, it's a vernier scale, and some of them read differently. Mine, you double the arc seconds, and then, so in this particular case, we'd have like 60.8 arc seconds. Well, if you minus 60 from that, you'd get left with 8 arc seconds, and you take that 60 arc seconds, which is 1 arc minute, and you add it to your arc minutes. So you'd have a 90/1308. And you do that with both these angles. Now, it's a mandatory face left, mandatory face right. And when you do that, in order to get the elevation angle, you subtract the face 2 from the face 1, and that provides you the elevation angle. So in order to obtain the zenith angle, you minus the elevation angle from 90. And so you'll do this for all of your sets. I turned 5 sets here. Now, I did not do a standard deviation. Basically, you can take this and you can subtract it from all of your zenith angles. Square that, add them all up, and get the square root, and then you can get the standard error of the mean. So basically, you know, how far away am I from the most likely number, and in this case, the average, right? So that's the most probable measurement, reaching to roughly about a 95% tile confidence. So what I did is I calculated what the curve was, or how much drop would be expected just geometrically from the tangent plane. So I took the distance in miles, I squared them and multiplied it by 8 inches. This is just 8 inches in decimal feet. That is 1,509.87. That's just geometric, no refraction. Now, I calculate refraction at the time of the observation. The coefficient that I came up with is a 0.153. That refraction angle would be a 3 minutes, 9.9 arc seconds. And that, if you tangent that out, that would be 231.37 feet. So I had 231.37 feet of lift on that target. Now, how do you obtain how much refraction you measured? Well, you take the cotangent of that zenith angle. You multiply it by the distance in feet, and then you add in what the expected geometric drop would be, and then add in your total observation height. Now, that brings me higher than the published elevation of that particular peak, which can't happen, right? So then you subtract what the published elevation of that disk is from what you got out of this guy right here, and I get a difference of 231.37. The drop that I measured was 17 arc minutes and 29.3 arc seconds, and if you tangent that out, it's 1,277.94 feet. So I'm 1,297, basically almost 1,278 feet from flat Earth. So, and this would be the flat Earth zenith. And this is pretty easy to figure out. It's just a basic right triangle. So this is what I measured. This is the data from that. This is science. This is observable. This is measurable, and this is repeatable. As you can see, I've done this several times to the same peak, and I'm coming up with very similar numbers. So last week, my average was an 89.28.21. This week, my average was an 89.28.29.3. So really close, but I'm definitely not getting close to a flat Earth.